Welcome to solverfy.
This is the answer to Chapter 19, problem number 73 from the Smith Organic Chemistry textbook. And this problem discusses warfarin. So it says, although it was initially sold as a rat poison, warfarin is an effective anticoagulant used to prevent blood clots. Label the most acidic proton in warfarin and explain why its pKa is comparable to the pKa of a carboxylic acid. Okay, and so in order to do that, I'm going to have to draw some resonance structures. This proton here is actually the most acidic proton. And the reason for that is this. So if we deprotonate that proton right there with some base, we get this. And again, just bear with me. I'm going to draw these resonance structures. So there will be a couple moments of me not saying anything. Okay, so this oxygen has been deprotonated. So there's now a negative charge there. It's always a good habit to put lone pairs everywhere. But so anyway, this is our first resonance structure. Well, yeah, so this is our deprotonated oxygen. And so we can envision a resonance structure where these electrons add here, and these electrons revert to this carbon. And so that is going to look like this. Oops. Okay, so we now have the oxygen double bound to a carbon. We have a lone pair on this carbon and a negative charge. And we can draw from here a third potential resonance structure. So again, just give me a moment to draw this. Okay, well, actually, I should, before I start drawing everything, I should talk about what's going to happen. So this part of the molecule is unchanged. Okay, but so to get to this third resonance structure, what we would have happen is these electrons could add in here to form a new double bond there. And this double bond can break. And so if that happens, we have a double bond here and a single bond here. And so this oxygen now has 3 lone pairs and has our negative charge seated on it. Okay, and so these are the important resonance structures here. So if we were to label these A, B, and C, what you see is that in A and C, we have 1 carbon-oxygen double bond and 1 carbon-oxygen single bond where the oxygen has this negative charge on it. And so this is exactly like a carboxylic acid. So exactly like a molecule where both of these oxygens are bound to the same carbon. They just happen to be bound to different carbons this time. And there is that structure B, which is sort of an intermediate resonance structure. But looking at A and C, we have these structures where one of the oxygens has a negative charge on it, and the other oxygen has a double bond. And so that is what makes this molecule's pKa so similar to a carboxylate ion. And the other thing that's going to make this such a strong acid comparatively, such a low pKa, is that we have conjugation in these systems where the double bond that does exist in A and C is in conjugation with the other double bonds in this molecule. And so that's going to really strengthen the ability of this deprotonation to happen, which is another way of saying it's going to make that proton that we labeled in the beginning of this problem much more acidic, because when it's deprotonated, it's not that big of a deal. This molecule can delocalize that negative charge pretty efficiently. And so that's the answer to chapter 19, problem number 73.